Let's now talk about mixtures of gases. First of all, for any gas, whether it's pure or a mixture of substances, if it's behaving ideally, then pressure times volume will be equal to number of moles of gas particles times R times C. PV equals nRT is applicable. So we can solve for the pressure of the gas by rearranging this equation. We simply divide both sides of this equation by volume. So pressure is equal to nRT over V. The pressure that the gas would exert is nRT over V. Now, if we're dealing with a mixture, we can define what's called a partial pressure. And that would be the pressure that a component of the mixture would exert if it were alone. Okay, so if you imagine the gas mix, the one component of the gas mixture were alone in that mixture, if you can somehow wave your magic wand and make the other molecules disappear, then the pressure that that component of the mixture would exert is called the partial pressure of component A. Well, the formula for partial pressure would just be moles of A times RT over V. It's the same because now the total number of moles would just be whatever the moles of A you would have, and the pressure would just be, you would call that pressure the partial pressure of component A. So partial pressure of component A, as you can see, would just be N sub A RT over V. So it's very similar to the formula for the total pressure. Okay. Partial pressure of component B would be moles of B times RT over V. Okay. So that would be the formula for partial pressure. Now, if you have a gas mixture, like I said, PV must be equal to N total times RT, or you can say P is N total times RT over V. Divide both sides here by V, okay? So, but N total, this N total is just moles of A plus moles of B plus moles of C or whatever. You add up all the moles of the components you have. So you can replace N total here by the sum of the moles of the components. And then you still have that RT over V over there. Well, the distributive property says that, okay, a little math review here, you, this expression over here means that if you multiply, that is equal to N sub A times RT over V plus N sub B times RT over V plus N sub C times RT over V, and so on, right? So this is just this expression right here. If you look at it closely, N sub A times RT over V, that's just the partial pressure of A. N sub B times RT over V, that's just partial pressure of B. In other words, what we're saying is that the total pressure of a gas mixture is just the sum of the partial pressures of the components. So imagine each of those components as if they were alone, calculate their pressure, and then just add up all their pressures, and that should give you the total pressure of your gas mixture. So the total pressure of a gas mixture is equal to the sum of the partial pressures of the components. P total is equal to P sub A plus P sub B, and so on, and that is known as Dalton's law. All right, so let's apply Dalton's law to this one. What are the partial pressures of oxygen and nitrogen in a 25-liter sample containing 1 mole of oxygen and 4 moles of N2 at 300 K? What's the total pressure? Well, let's solve for partial pressure of oxygen. It's moles of oxygen times RT over V. Okay? So moles of oxygen in this case is 1.00 mole times R, which is 0.08206 liters times atmosphere per mole per Kelvin. That's your R. Temperature is 300 Kelvin, 300.0 K, divided by the volume, which is 25.0 liters. There's your volume right there. So liter cancels out, Kelvin cancels out, mole cancels out. That gives you the pressure in atmosphere. Let's calculate that. 1 times 0.08206 times 300 divided by 25, 0.9847. Okay, I'm going to keep an extra digit there. It's 0.985 atmosphere. 3 significant digits. I have 3 sig figs here. Okay. and 3 sig figs in my volume, 4 sig figs in my temperature. In my R, I have 4 sig figs. Okay. Let's calculate partial pressure of N2. Partial pressure of N2 will have 4 moles, right? So do the same thing, except over here, instead of 1, you put 4. So the value you get should be 4 times whatever 0.9847 is, right? So this is just going to be 4 times 0.9847. You can do it the hard way, or you can just visualize it that you have 4 times as many moles of nitrogen, so you put a number 4 here instead of 1, okay? So let's see what that is. 4 times 0.9847, that would be 3.939. 9388. So okay, 4 sig figs, so 939. 3 sig figs, okay, atmosphere. So if I want to get the total pressure, I simply add the partial pressure of O2 and N2. Dalton's law of partial pressure says the total pressure is pressure of O2 plus pressure of N2, and that should just be equal to 0.9847 plus 3.939 equals 4.923 sig figs atmosphere. What's another way we could have done this? We could have just said total pressure is N total times RT over V, and you would have gotten, for N total instead of 4, you would have gotten 5 moles, right? Instead of 4 and 1, which we use for each component, we can just use the total moles, which would be 5, and you should see that this is going to be 5 times 0.9847 atmospheres, right? And so 5 times 0.9847 is 4.92 atmosphere. Same answer. So that's an illustration of Dalton's law.